This is Euclid Book 3, proposition number 8, and this is part 1, believe it or not, because there's going to be several parts to this. This is going to be one super humongous proof. Sorry about this, folks, but there's going to be a giant circle here. I made it 3 inches in diameter. Okay, you can make it any size, but I would recommend at least 3 inches or better, mainly because otherwise you wouldn't be able to fit all these lines in here. And Euclid says, I want you to pick a point, and it's going to be called point D. Here's point D. And then he says, I want you to draw a line from point D to point G, through point M, and through point A. Now, before you can draw this great big line here, you have to find the center of the circle, which is M, and you have to use Euclid Book 3, proposition number 1, to do it. So, use Euclid Book 3, proposition number 1, to find the center of this circle, and it will be M. Once you do, then you will draw a line from point D, through point G, through point M, and down to point A. Whew. And then you will draw a line from point D through point K and all the way down to E. You will draw another line from point D all the way through L and all the way through F. And then you will draw a line from point D to point H and down to point C. So far, so good. Now then, what is Euclid trying to prove? Well, that gets to be a kind of a complicated. All right. Line DA, D to A, is greater in size than line DE. And line DE is greater in size than line DF. And line DF is greater in size than line DC. Now, you probably ought to remember a lot of this from Euclid Book 3, proposition number 7, where we prove something similar. Not the same, but similar. Okay? Now then. But that's not all Euclid wants to prove. Euclid wants to prove that line DG is the smallest of these 4 lines right across here. Now, I'm going to show you these 4 lines. So we've got DG here, DK here, DL here, and DH. DG, DK, DL, and DH. And he's saying that when we prove all these other lines to be whatever they're supposed to be, then he said we're going to also prove that DG is shorter than DK, and DK is shorter than DL, and DL is shorter than DH. That would make DG the shortest of these 4 lines, and it's shorter than DH, which happens to be the longest. Whew. Yeah, I bet you're sitting there going, oh my gosh, how are we going to prove all this? All right. Well, the first thing we're going to do is we're going to draw a bunch of other lines. That's right. We're going to draw ME, MF, MC, MK, ML, and MH. All right. Now, I know I went a little fast on that. Where is ME? Well, ME is right here, from M to E. We're going to be drawing lines from the center radius here to the outermost edge here. So we're going to draw a line ME, MF, MC, MH, ML, MK. We're going to draw all those lines. And when we do all of this, you're going to form a bunch of triangles. That's where our proof begins. All right. Let's start with AM equals EM. Well, here's AM here, and here is EM here. And why are they equal? Boy, this goes all the way back to the first proof of Euclid, where he said all radii of a circle are equal. So, AM and EM are going to be equal because all radii of a circle are equal. We're going to add the length of MD to both AM and EM. Now, where is MD? Well, here's the length of MD. Okay, we're going to add that length to AM and EM. So now, we can say that the length of AD, which this is A, this is D, the length of AD is the sum of the length of EM, here's E, here's M, and the length of MD. Now, we can say that because we can already say that the length of AD is the length of AM plus MD. Okay? And since we already know that the length of EM and AM are exactly the same, we can also say that if you add the length of EM and MD together, you're going to get the length of AD. Alright. Now this also means that the length of EM plus MD, here's EM here, and the length of MD here, is going to be greater than the length of ED. And how do we know all this? Because of Euclid Book 1, proposition number 20. But we can go on, because now we can say that the length of AD, here's AD here, is greater than the length of ED right here. Okay? Now then, we can also then therefore say that the length of ME is equal to the length of MF. Well, here's ME here, here's MF here, and they're equal in size because all radii of a circle are equal. Now, if we were to add the length of EM to MD, well, here's EM and here's MD, and we were to add the length of FM to MD, FM to MD, they would be exactly the same size. Alright, the angle of EMD is greater in size than the angle of FMD, which means that the length of ED is greater in size than the length of FD, FD. ED here is longer than FD right here. And that's because of Euclid Book 1, proposition number 24. And that is where we're going to stop in this particular video. And I will cover this in the next video. Stay tuned.